Hi everyone. In one of the previous lectures, I discussed a level shifter circuit, and I think one of you emailed me, does this work for analog signals as well? The answer is no. You have to understand the circuit that I discussed in that video, in that lecture, is what we call a CMOS level shifter or a digital level shifters. So those level shifter circuits typically operate this way. You feed an input digital signal with say the logic 0 with a voltage level VH and a logic 1 represented by a voltage level VH. The output signal will have same logic values. The logic does not change. A 0 at the input is transferred as 0 at the output. But the voltage levels representing those logic will change. So that's what we meant by level shifting. Okay, so the voltage VHO and VLO represent the logic 0 and logic high voltage levels of the output. That will be different. What is the motivation for them, and all of that I have discussed in the previous video itself. I recommend you watch that. Now in this lecture I will talk about analog level shifters. So circuits which can shift the DC voltage levels of analog signals. Mainly, I will focus on those circuits which operate on low to mid range frequencies, typically in the order of kilohertz to a few tens of megahertz. Mainly, I'll be discussing circuits which uses op-amps. Now, as you increase the signal frequency to very high frequencies, then there are a different set of circuits. In fact, as you go to higher and higher frequencies, the circuit architectures become much simpler. Okay, a differential amplifier, a single stage differential amplifier will do the job for you. So I'll talk about that in a different lecture. Right now I'll focus on low to mid range frequency. When I say low to mid range, typically I'm referring to kilohertz to few tens of megahertz of frequencies. Okay, how do you design a voltage, how do you design a circuit which can shift the DC voltage levels? So we'll look at different variations of such circuits. So where do we need that? Where do we need such circuits? Very quickly, typically let's say you're an embedded system designer who has to have awareness of voltage levels when you're interfacing different boards, okay, different circuits or different boards. So say we have a sensor IC which is sensing, and it can be sensing an audio signal, or it can be sensing, it's a sensor IC, so it can measure temperature or pressure or any other quantity of interest. For the time being, let's assume that the sensor's output, typically it's true for audio signals, I can assume that it produces a sinusoidal output with a certain peak and a DC voltage. Let's call VCMI as the input common mode level. The goal of this level shifter is two things. One, it should be able to change the DC level of the signal to some other level. Let's call it VCM or VCMO. The DC level should be shifted to VCMO, some other level, and if possible we should also be able to amplify this peak voltage. So the amplify this AC part. Okay, the signal has, it's a superposition of DC and AC. The DC level should be changed, and also if possible we should look at topologies which can also amplify the peak level. Now why is this important? Because you may be driving some signal conditioning circuits. It can be filters or it can be ADCs. For those circuits, for proper operation of those circuits, typically they may have some requirements. What should be the input DC level and what should be the peak to peak input levels that it can properly operate on. Okay, so to meet these constraints you may need an interface circuit. These interface circuits is what we will discuss right now, which do two things. One, it adjusts or it changes the peak levels, which does an amplification operation for the AC part, and also it shifts the DC level. Immediately the moment I say you want to shift the DC level, the one thing that you can immediately think of, if you have taken any basic course on circuit design, discrete amplifier design, or even an integrated circuit design, is to AC couple the signal. You take the sensor's input, pass it through a capacitor and a resistor like this. If you do that, what you are doing is that you block the DC. VCMI is fully blocked, and if you see this AC coupled circuit, it's a high pass filter, right? It's a high pass filter, and for this high pass filter, the pole frequency is given by 1 by 2 pi RC. If the cutoff frequency is 1 by 2 pi RC, you should ensure that your input signal is in this range. That is, the input frequency is greater than the pole. So Fin should be greater than 1 by 2 pi RC. If you ensure that, then the peak value at this or across the resistor will be same as the input. But now what will be the DC value at the output? In this circuit, the DC value will be 0. But if I want to fix it to a value, say VCM, I can simply, instead of connecting the resistor to ground, I can simply connect it to VCM here. If I do that, as far as VCM is concerned, you can apply principle of superposition to find out the voltage here. Okay, voltage at this node. Okay, for the signal at this point to the resistor, it's a high pass filter. As far as VCM is concerned, if you look at this part, if you look at it this way, from the resistor to the capacitor, it's a low pass filter. So the DC voltage at this node will be same as the DC voltage at this node. So therefore that DC value will be VCM. So now I've accomplished the DC level shifting. In the simplest circuit to do a DC level shifting is just to use a high pass RC filter as shown here and connect the other end of the resistor to a common mode voltage VCM. Still, this circuit doesn't do amplification. We have to think of how to amplify it after that. Okay, we have to come up with some way to amplify it as well. But there is one problem with this circuit, is that what if I'm directly driving the circuit to a load? Eventually the filter or an ADC will appear like some resistive load, or it can also appear like a capacitive load. Let's say it appears like a resistive load, then that interferes with the pole location for the circuit, and also it interferes with the DC level. Now that DC level at this node, because of the resistor loading effect, it changes with the load resistor, and you don't want that. So how do we fix this? So that's what we look at a set of circuits and very logically arrive at, we will see how all the circuits make proper intuitive sense. So one classic way of fixing the loading problem is just to add buffer in between. So that's what I've shown here. So if you see, this part of the circuit is just a voltage follower or a voltage buffer. So at this node, we have changed the DC common mode level, right? If you choose your RC appropriately, meeting this condition, Fin should be greater than 1 by 2 pi RC, then the AC part of the signal fully is coupled to this node. And the DC level here is set by VCM. So then if you put a voltage follower, you are going to get the same voltage at this point, that is at the input. The input voltage and the output voltage will exactly be the same. Whatever is the non-inverting terminals voltage, that will be same as the output voltage as well. And whatever be the value of the load resistance, because it's an ideal op-amp, it's going to give you the same voltage. It's going to be independent of the load resistor. So that's what a buffer is supposed to do. Okay, so what you get at the output is going to look like this. VOCM will be the output common mode, and the peak value will be same as the input signal level. And VOCM in this example is exactly equal to VCM itself. VCM is the input DC, which is nothing but, which is set by the voltage that is connected to this resistor here. In fact, you can also think of a potential divider circuit or whatever. You can think of different variants, but I have shown a very simple circuit which can accomplish this. Okay, so if you look at literature, you might find circuits like this. You have a capacitor and resistors connected this way. You know, some say RX1 and RX2 and some VDD or V supply, and depending on some potential division, that will set the common mode value here. Okay, so you can think of all that, but I have just shown a very simple circuit. I mean, you can draw an equivalent Thevenin representation and show it this way as a single resistor and a voltage source. Okay, so that's it. So this is the first circuit, which is using a voltage buffer to fix it. Now there is one small problem with the circuit, that is nothing but, if you look at the circuit, the output common mode is exactly same as the input common mode. Sometimes you may want, for op-amp architectures, to decouple this. You don't want the same output common mode and the input common mode. Can you have different common mode levels? And the answer is yes, you can, and you can do that by modifying the circuit this way. In the feedback path, instead of connecting uh, the input and output directly, you can add a resistor this way, and then a current source connected from the inverting terminal to ground. Now first we'll analyze the circuit, see and what it is doing. So there are two parts of the circuit. One is the signal that's coming from the inverting non-inverting terminal, and then we have to see what is its contribution at the output. Then what impact does this current source have on the output? So you can easily apply the principle of superposition to find it out. So first let's assume the current source, we can open circuit the current and immediately see that we know what the output common mode is. The VOCM is directly equal to VCM itself. Okay, now the moment I connect this resistor, connect this current source, you can see that the impedance offered by this node is 0, because if you recall, for an ideal op-amp, if the op-amp is ideal, there is negative feedback in the circuit. Let's assume A is the amplifier gain. We know that this resistance seen here using Miller's theorem, you can say it is R by 1 plus A, and if A is infinity, you get 0 input impedance. I've already discussed this in one of the op-amp lectures. So which means all the current will flow through the op-amp, and since we know that the input current drawn by the op-amp inputs, whether it's the inverting or the non-inverting terminal, is 0, all this current will flow through the resistor itself, and the voltage drop across the resistor will be Ix into R. So the DC voltage of this signal, if you see the DC level, will be this node voltage is at DC level is at VCM. That's because of the non-inverting terminals DC. Non-inverting terminals DC is at VCM, and the output DC level is at VCM plus IXR. So the output level here is the voltage across the resistor plus the voltage at this node. So the voltage at this node to ground is VCM, which is also the voltage across the current source. Okay, and that is enforced by negative feedback. Negative feedback ensures that the DC voltage at this node, the resistors, the one terminal of the resistor, which is nothing but the non-inverting input of the op-amp, and is same as the DC voltage at the inverting terminal of the op-amp. Okay, so that sets it at VCM. But the output common mode, or the output DC level, is the voltage VCM plus the voltage across the resistor, which is Ix into R. So this way, if you see, I am able to change the output DC level. That is different from the input common mode level. So this gives me an additional degree of freedom. Now this resistor, if you see, I've written it as R here. Let's call it RF to distinguish from this resistor. So let's call this RF. Okay, so this resistor has no role to play for the input signal. So if you assume, we can quickly apply superposition and just remove this current source. And if you analyze this, because no current flows into the op-amp's input, right? As far as the AC signal is concerned, there is no AC current flowing in RF. The IAC current is 0. Okay, because the current in RF is always fixed to be equal to Ix. Okay, that's always fixed. So there is no AC component. So therefore, as far as AC signal is concerned, it will act like a short circuit. It will just behave like a voltage follower. So the output peak voltage will remain the same. So this is what the circuit is. The output peak voltage will remain the same, but the output common mode, DC common mode value, will now be different from the input common mode. It will be VCM plus Ix into RF. That's the difference. Now we'll try to add the amplifying characteristic as well. How do I turn it into an amplifier? It's an op-amp circuit with some very simple modifications. All I need to do is just put another resistor between VCM to the output node. Okay, so I've removed the current source for the time being. Okay, that current source gives you a freedom to set the output common mode to a different value than VCM. That's it. I've removed the resistor for the current source for the time being, and then put a resistor R1 between the common mode, between the inverting terminal to another. So let's for the time being call this ground. So now this circuit is immediately one can immediately recognize what this circuit does. It's a non-inverting amplifier. The gain of the circuit is 1 plus R2 by R1. Okay, so for as far as AC signal is concerned, okay, or in fact, since it's a non-inverting amplifier, it's going to amplify everything including DC as well. So here if you see, the DC value of the signal is VCM and the AC signal's peak voltage is V peak. At the output, if let's say this node was connected to ground, you would expect this signal, both DC and AC, to be amplified by the same factor, which is 1 plus R2 by R1 into V peak. So this node will be at VCM, DC wise. The output DC is value will be VOCM equals VCM into 1 plus R2 by R1. But we don't want this. We need to only amplify the AC part. I don't want the DC part to be amplified. That can be fixed by connecting this node to VCM. Instead of connecting it to ground, if I connect it to VCM, if you see, negative feedback will force this node to be equal to VCM. And I'm just analyzing the circuit, splitting it as AC and DC. If you see the DC wise, the non-inverting terminal DC voltage is at VCM. Inverting terminal's DC voltage will also be at VCM. Since this node is also at VCM, the current flowing through R1, DC current flowing through R1 is 0. So therefore the DC current flowing through R2 is also 0. So the output common mode DC will settle at VCM. So in this circuit, the output common mode is same as the input common mode, which is set by at this node, which is VCM. But the signal level, the AC part of the signal gets amplified by a factor 1 plus R2 by R1. That's the gain of a non-inverting amplifier. So you got the amplification and you are also able to change the DC level. Again, the same problem, we have a different DC level than the input DC level. If you see this Opamp, the input common mode of the Opamp is VCM. The output common mode or output DC level is also VCM. Can we decouple that? Can we have different common modes? The answer is yes. We just saw how to do it in the previous problem. Just put a current source. If you put a current source, so now if you see, the current has two paths to take. It can flow through the resistor R1 or it can flow through the resistor R2 also. But if you again use Miller's theorem, the input impedance offered by this part, op-amp and resistor and feedback, is 0, which means all the current has to flow into this combination of op-amp and resistor. The resistor offered by the resistor R1, so now this current Ix has two paths to take. One, it can go through R1 or it can go through R2. But the path through R1 is not an enticing path because the impedance offered by the op-amp and resistor R2 is 0. So all the current is going to flow through the op-amp itself, this op-amp and the resistor and feedback. So the current will fully flow through R2 and the voltage drop across R2 will be Ix times R2, the DC voltage drop. So I have connected this node to VCM and so this node comes to VCM by negative feedback. So because the DC voltage at this node is at VCM, the output DC is nothing but VCM plus Ix into R2. Now remember, I didn't mention it previously. Ix can be negative, which means I can just change the direction of Ix in this way. I mean, I can connect from VDD to this node. Okay, and then this voltage can be lower. The input common mode, the output common mode or the output DC level can be lower than the input DC level or it can be higher than the input DC level. That can be set by choosing Ix value. It can be made positive or negative, meaning it can be a sinking or a sourcing current. So now I have accomplished all that I was talking about. That is, to a circuit which can change the DC level at the output and also be able to amplify the AC part of the signal, input signal. And in this circuit, we saw a variant where the output and input DC levels can be set independently, okay, by using an extra current source Ix. Okay, another thing, one small detail, again I wanted to, probably I didn't discuss it when I was talking about how this, if you see by how the current Ix takes fully flows through R2, you can see by virtue of negative feedback, the voltage across the resistor R1 is always 0, right? So this node is set to be equal to VCM, and this node is already connected to VCM. So the current through R1, the DC current through R1 is 0. Okay, it's 0. So that's why the current Ix cannot flow through this, and the op-amp's negative feedback action doesn't let it flow through that. So all the current has to flow through R2 itself. That's it. So that's it. I've discussed a circuit which can do DC level shifting and also amplification of the AC part. There is one other problem with the circuit, which is if you look at the input signal, the op-amp's input is also going through a sinusoidal variation, right? As your input signal is changing, there is not just DC at this node, there is also an AC signal. So which means this node is actually undergoing a swing. Both the input terminals are undergoing a swing, and the current source sees that swing. Okay, and the op-amp's input also sees that swing. So which means you need to have what we call a large input common mode range. So when we talk about op-amp design, I'll talk about this spec, what is ICMR. So the op-amp needs to have a very high input common mode range. So generally it's not preferred. It complicates the design. Okay, so can we resolve this problem? So that's one problem with non-inverting amplification, is that the input common mode range should also be reasonably good. To solve that problem, what we normally do is we go for an inverting amplifier configuration. So if you see an inverting amplifier configuration, so let's say I connect this node to VCM, and this is connected to R2 and R1 here. So even though the signal is, there is a huge the signal is swinging at this node, if you see the inverting terminal is always calm, it's always at VCM. The output signal level is an amplified version. Of course, there is a phase inversion. It's an inverting amplifier. It's minus R2 by R1. There's a phase inversion. The amplitude is multiplied by a factor of R2 by R1. Okay, which can be greater than 1. Which can be, you can choose it in such a way so that it's equal to 1 plus R2 by R1. The gains can be matched in both the op-amp topologies. The advantage of an inverting amplifier is that the input terminals, the common mode range doesn't have to be so high. The ICMR, the input common mode range, that's the range over which the op-amp should operate like an amplifier. It should give you all the properties of an op-amp, give you infinite gain and negative feedback, which also ensures negative feedback is active and all that. Okay, so you shouldn't saturate the op-amp or decrease the gain and all that. So inverting amplifiers are often preferred for this reason, because your input common mode doesn't have to change so much. So that's what, instead of applying the signal to the non-inverting terminal, you can apply the signal, you can AC couple the signal through an RC filter shown here, directly at the inverting terminal through a resistor R1. Now if you see, the pole location is your resistor R1, the impedance seen at this node is nothing but R1, right? Because the op-amp is a negative feedback, the resistance seen here is 0. So which means the resistance seen here will be R1 plus 0, which will be R1 itself. So the pole location will be, that R1 comes in parallel with R. So the pole location will be 1 by 2 pi R1 parallel R into C. So you should ensure that this pole is smaller than Fin. That's the only thing you need to do. If you ensure this condition is met, then you can fully couple your AC signal to this node. It's fully coupled to this node with a peak value of PP, and the DC can be set by connecting this end of the resistor to VCM. Okay, so sorry, you can't directly do that. So you can choose an appropriate voltage here, so which will ensure that the DC voltage signal here also comes to VCM. Okay, actually I think I'm very sorry. If you connect this node to VCM, it will work, the circuit works. If you connect this node to VCM and the non-inverting terminal also to VCM, the negative feedback will ensure the inverting terminal voltage is at VCM. Then you end up getting a circuit that looks like this: R, VCM, and R1 and VCM. Okay, so the voltage at this node if you see, there is no current flowing in this part. DC wise, there is no current between these two nodes. Okay, through the resistor, these two are in series. These two, for DC, these two are in series, R1 and R, and there is no current flowing through them. So the potential at this node will also be at VCM. Okay, you can apply superposition also and show that it will come to VCM. So the DC value at this node is at VCM, and on top of it you have a sinusoid whose amplitude is V peak. Now the output voltage, first we'll see the AC part. AC part gets amplified by a factor of R2 by R1, right? It's just an inverting amplifier like this. So that's what I've shown here. It's an inverting amplifier. The peak voltage is now Vp into R2 by R1. But the DC voltage, as far as DC is concerned, if you see, there is no DC current flowing through R1 because this node is at inverting terminal is at VCM and this node is also at VCM, right? Which forces both the ends of R1 to be at VCM volts. So therefore the DC current flowing through R2 is also 0. So VOCM, the output common mode, is actually equal to the input common mode, which is VCM. Okay, so the output voltage, the output signal has a DC level which is equal to VCM and the AC level which is R2 by R1 times V peak of the input level of the input peak. Now if I want to independently set the input and output common modes, I can always add another current source and connect it this way. Let Ix be this current. Then I can ensure I can ensure, because again for similar reasons the current through R1 is 0. Okay, so all the current will flow through R2. The output DC level will be VCM plus Ix times R2. Now I can choose Ix in such a way so that the output common mode level can be either greater than or lower than the input or the input common mode of the op-amp. So that's it. This is all about the op-amp based analog level shifter circuits. So I've discussed some flavors of some variants of this AC coupled op-amp based circuits, which allows you to choose the DC voltage levels at the output and also provides you some amplification for the AC part of the signal. Okay, yeah, thank you.